Hello calculus fans, and welcome to part 2 of section 8.3. Section 8.3 is a pretty large section, so I cut it into two parts. The first part dealt with hydrostatic pressure and force, and the second part of section 8.3 deals with moments and centers of mass. In this section, we're going to use calculus and a principle from physics to determine moments and centers of mass of one- and two-dimensional objects. For three-dimensional objects, you're going to have to wait until calculus 3 when you have multivariable calculus. But first, we need to talk about some terms. So in finding the center of mass or balance point of a one-dimensional system, we're going to start off with a one-dimensional system. Okay, so the center of mass is the balancing point when masses along a line are mounted on a fulcrum. And the moment of an object A is equal to the mass of A times the length of the lever arm. Length of the lever arm, which we'll think of as a distance. So you could really think of a moment, you could think of it as mass times distance. So let's see how to find the center of mass of a one-dimensional system. So suppose we have two objects with mass m1, which we'll put right here, and mass m2. They're placed on a seesaw, or teeter-totter if you prefer, at distances d1 and d2 respectively. So we have something like this picture here. And just as you know from experience in maybe first grade? I don't remember what grade it is when we did this. Maybe younger, maybe preschool. But you'd have a teeter-totter here. And if your friend is heavier than you, if you wanted this to balance, you'd have to come up closer to the fulcrum, right, where your friend was further away. So to balance the seesaw, we need mass 1 times distance 1 to equal mass 2 times distance 2. So we need these to be the same. This is called the law of the lever. This is proven by Archimedes. He lived between 287 and 212 BC. He is often regarded as the greatest mathematician of antiquity, and always, whenever there's a list of the greatest mathematicians in history, he's almost always in that list. It's some pretty incredible things. So let's just suppose that this fulcrum right here, this balance point, let's suppose this is located at the origin. So we'll think of this as a number line. This is the origin. So we put a little 0 right here. Okay, so if that's located at the origin, then we would have distance 1. So if this is a number line, this distance 1 would be equal to 0 minus x1. So we'll call this, before I do that, maybe we better label these. Let's do this in black. Let's call this 0. We'll call this point here x1, and then this point here x2. Okay, so again, we'll think of this as a number line, right? So distance 1, this distance, just like on any number line, the distance is going to be the number on the right, number to the right, minus the number to the left. That'll give us a distance, right? So distance 1 is going to be 0 minus x sub 1. So distance 1 is going to be 0 minus x sub 1, which equals negative x sub 1, which makes sense because this will be a negative number, right? If this is 0, this will be a negative. So the distance would be minus the negative number. Okay, so that's distance 1. And then distance 2, of course, distance 2 is going to be x2 minus 0. So distance 2 is going to be x sub 2 minus 0, which is just x sub 2. And then using the law of the lever, mass 1, distance 1 equals mass 2, distance 2. Sometimes people call this law of the lever, but doesn't that sound weird? Lever? I think it's law of the lever. Okay, so if we plug this in, mass 1 times distance 1, well, distance 1 is just negative x sub 1. So really this would be negative m sub 1 x sub 1, right? If I just plug these in, remember, m sub 1, d sub 1 equals negative x sub 1. So I multiply those together so I get a negative out here. And that will be equal to m sub 2 times d sub 2. D sub 2 is just x sub 2. Okay, so that means that if I were to just add this to each side, I'm just going to add this to each side, I would get 0 equals, and then those added. I'm going to put it the other way around, though, so I'm just going to write it like this. M sub 1 x sub 1 plus m sub 2 x sub 2 equals 0. Right, that just follows directly from here. If I just add m sub 1 x sub 1 to each side, we'll get this. Okay, and then this right here, which is right here, this number is called the moment of the system about the origin, and is denoted by m sub 0. We can define this moment about the origin this way. We can say the moment of a system about the origin containing these masses, m sub 1, m sub 2, all the way to m sub n, so if there are n masses located at these corresponding points, well, the moment about the origin is just m sub 1 x sub 1 plus m sub 2 x sub 2 plus dot 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 plus m sub n x sub n. Or you could write this more concisely using summation notation. Just say it is the summation from I equals 1 to n of m sub I x sub I. What this is, the moment about the origin measures the tendency of the system to rotate about the origin. So some of you who have studied physics may think this sounds a little bit familiar. It sounds a little bit like torque. So if you add gravity into the system, then you have torque. A moment is said to be a feature of the system itself. So moments just deal with masses and distances, where torques deal with forces and distances. But it's very, very similar idea. Okay, so the moment of the origin measures the tendency of the system to rotate about the origin. So that means this. We could say, so if m sub 0 is 0, when that happens, the system is balanced and won't rotate. One thing that happens when I make these videos is they lack all the interaction you get in the classroom. So the classroom is just so much easier to keep people alert and entertained and awake, mainly awake. These videos are so hard, so sometimes I test it out and sometimes these videos don't go well. So I'm going to give you an example. I had a test today. I had 3 of my star students. They started off in class, and at least 2 of the 3 were looking pretty motivated to learn about center of mass. So things were looking hopeful at first. You can see 2 eager students, eager to learn, and 1 that was, not so eager. But you can't have everybody. You can't have everybody on board initially. But by the time we got to the end of page 1, something terrible had happened. 1 student already left, and the other 2 are sound asleep. So I have to apologize. I just don't know how to make these videos any more exciting when we don't have that face-to-face interaction. Hopefully all of you listening are doing better than my 3-star students. If not, maybe this next problem will pique your interest. We've got a very exciting one-dimensional system shown below. As you can see, we've got our fulcrum here, and we've got an object here of mass 1 and this little object here of mass 2. And we're going to think this is a one-dimensional system, like a number line again. So we'll call this x bar. We'll call this x sub 2. We'll call this x sub 1. In x bar, we want this to be the coordinate of the balancing point. So this is the center of mass. So right now, the system is perfectly balanced. And this x bar is that coordinate. So m sub x bar is 0. So the tendency for this system to rotate about x bar is 0, means it's at rest, right? The tendency to rotate is 0, it doesn't exist, so this is just at rest. So this just means the moment about x bar is 0. Okay, so with this in mind, we could say this, right? Because this says mass 1 times distance 1. So this distance here is just going to be x bar minus x1 will give us that distance. So mass 1 times distance 1 equals mass 2 times distance 2. So distance 2 is going to be x sub 2 minus x bar. Okay, so from here, let's go ahead and distribute m1 and m2 through the parentheses. Okay, so that gives us this. And then what I want to do is get the x bars on the same side of the equal sign. So I'm going to basically add this to each side to get the x bar over here. And I'm going to also add this to each side to get this over here. Okay, so that will result in the following. Okay, so that gets us here. And now what I want to do, we're basically looking for the coordinate, this x bar, the balancing point. So I'm going to factor out x bar from here. Okay, so factor out an x bar. We'll get m sub 1 plus m sub 2 equals all of this. Then, of course, if we want to get x bar by itself, I'm going to divide both sides by this. We'll get x bar equals m1 x1 plus m2 x2 divided by m1 plus m2, so the sum of the masses. So when you look at this is the formula for x bar, and look at this up here. This is just the moment of the system about the origin, and this is the sum of the masses. Okay, so that gives us the formula for x bar. And of course that extends to any number of masses, right? We just have mass 1 and mass 2, but you can see it would extend indefinitely to any number of these, right? So this extends to any number of masses, right? So in other words, if there were a third mass, this would say plus m3x3, it would divide by m1 plus m2 plus m3, okay? Now sometimes students will ask me, what about, we're finding the center of mass. What's the difference between the center of mass and the center of gravity? Okay, it's a good question. For most practical cases, it doesn't matter, but if you think of like an extreme case, let's say we've got this right here. So this is the Earth here, and let's say we've got this let's say we've got this metal rod, this huge metal rod. It's out in space, and it is, something like this where it's got a uniform density. So it's a uniform density, just some metal rod. Well, if it's uniform density, that means that right in the middle of this thing would be the center of mass, right? So there's a center of mass like right in the middle of it, let's say. Center of mass. Well, in this case, because the Earth, the mass of the Earth would pull, the gravity would pull on this end more than this end. So the center of gravity would be pulled down a little bit below the center of mass. So in a case like this, in this extreme case, the center of gravity is down here because the acceleration due to gravity is going to be more here than it is up here, right? Because we're closer to the center of the Earth here. So the center of gravity is going to be below the center of mass in a case like this. But for practical purposes, there's not going to be a noticeable difference. So we're just going to always find the center of mass in this class. But for all practical purposes, it's also the center of gravity. All right, so that brings us to a box with some formulas. And it says the center of mass of a system along a straight line. And one thing to notice about this is the center of mass. This is in one dimension, right? So basically the center of mass equals x bar. This is in one dimension, so this is one dimension. Like just along a straight line. The center of mass is just x bar. I don't know why that x looks so bad. Let me try this again. Center of mass, x bar. And what you've got here, to find this x bar, this is just the sum of the moments, and this is the sum of the masses, right? This is the sum of all the masses, and this is mass times distance, so this is the sum of the moments. So just make a quick note about that. This is the sum of the moments. This is the sum of the masses. And we can't just cancel these masses here because this is the sum of mass times distance, right? And these masses will be different. So there's no factors that can be canceled here. So it is just this divided by this to find these. And the shorthand notation you see a lot of times is something like this. You say x bar equals m sub 0 over m. And what we mean when we see this is this m is really, let me say, there's a lot of shorthand in this section because otherwise the formulas get a little awkward. Just a lot. There's a kind of a lot. So when we see this in this formula, it means the sum m sub I means the total mass, the sum of the masses. All these mean the same, right? This is the total mass, or the sum of all the masses, and this is sum of the moments, or the moment of the system about the origin. So this is just kind of a shorthand notation that means the same as this. This brings us to example 1. So we've got some masses and some locations where these are. And so what I'm going to do for these points, I'm just going to draw a number line, and at these points put these masses. Then we'll find a picture of it, and we'll find the center of mass for the system. And the picture just makes it a little easier to see what we're doing. So I drew a little picture in here, and I try to make these look proportional to their mass. It's got these masses of 4, 2, 6, and 7 kilograms located along here on this number line. We want to find the center of mass for the system. So in other words, if you could put like a little balance point somewhere along this number line where this thing would be in perfect balance, where would it be? So to find it, we can use our formula from above. We need to find the sum of the moments. So the sum of the moments, you look at the formula up here, we'll see that it is going to be m1 times x1 and plus m2 times x2 and so on and so forth all the way through here. Notice that when I introduced this idea of a moment, I said basically it's mass times distance gives us the moment. Technically, it's not quite correct because moments are vectors. So we have a plus and a minus on these distances. So as long as we just use this formula, everything will be fine, because then we have these x coordinates, right? So m sub 1 times x sub 1. So sometimes the introductory idea is just think of mass times distance. But when we use a formula, some of our, quote, distances will be negative, because we're just using this, right? We're using these x coordinates. So when I do this, I've got wherever there's a mass, we need to put this in the formula. So if there's not a mass here, we don't need to use it, right? The formula calls for a mass. So we've got 4 masses. So this is going to be mass m1 times x1, right? So this, when we plug these numbers in, we're going to get 4 times negative 3 plus 2 times 1 plus 6 times 2 plus 7 times 4. So we're just using this formula m sub I, x sub I for each of these. And we have to divide this by the sum of the masses. So that's going to be 4 plus 2 plus 6 plus 7. So we go through the math here. We get negative 12 plus 2 plus 12 plus 28 over 19. And this gives us 30 over 19, or approximately 1.58 roughly. So what that means is, if you go over here to 1.58, right at that point. So 1.58, so maybe right around here. We drew a little balancing point, a little fulcrum here. This right here is where this system would balance. So there's heavier masses here, but they have less of a distance. Smaller masses here, but a much larger distance. So the balancing point would be right around there, 1.58. Okay, so finding the center of mass in a one-dimensional system like this it's pretty simple. We just do like what we just did for example 1. Okay, so for two-dimensional systems, it gets a little more complicated, and there's two cases. Sometimes you have a finite number of points, which then it's just sort of like what we just did, but you also have to go along the, say, the vertical distance, right? The vertical direction if it's going to be a two-dimensional system. But the other case is when you have an infinite number of points, like, for instance, between a couple of equations, where you have like a little region of space stuck between a couple equations, then it gets a little trickier. Then we need calculus for that. But let's take a look at the easier case first. So find the center of mass of a two-dimensional system. And I need to just mention this is for a finite number of points. Finite number of points. And it's going to be very familiar or similar to what we just did. So the center of mass, I can tell you, in this case, it's going to look like a point, x bar, comma, y bar. X bar is just what we did, and then y bar is going to be the other part of it. So this is it's a center of mass in 2 dimensions. So what we're going to find now is the center of mass, 2 dimensions. And again, this one's for a finite number of points. Okay, so I'm going to draw a picture here, and then we'll talk about how to find the center of mass. I have to move this up to get a good picture. So consider this system. We've got 3 masses, and think of this as being able to rotate along this y-axis. So think of it as these pushing down into the screen and then this coming up out of the screen, like it could rotate here about the y-axis. But also, we've got another dimension, so we could think of it as being able to rotate also, or spin, rotate about the x-axis. So we have to consider both of those. So to do it, let's say, so we've got the y-axis, we've got the x-axis, and let's think of this mass 1, and it's got a distance here going to the y-axis. Mass 2 has this distance going to the y-axis. Mass 3 has this distance going to the y-axis. So let's call this x sub 1, x sub 2, and x sub 3. And then we've got to talk about 2 things. The first thing we can talk about is m sub y. And this is the moment of the system about the y-axis. So m sub y, moment of the system about the y-axis, just like when we had m sub o, which was the moment of the system about the origin in the one-dimensional case. What this is the tendency of the system to rotate about the y-axis. And the formula for this, as you could imagine, it's going to be the sum as I goes from 1 to n of m sub I x sub I. It's the sum of these moments here, right? Like you could think of this moment 1 and or mass 1 and mass 3 would tend to make this rotate, right? Like you could think of it as like into the screen. Where this, around, like if we could rotate right here, this would tend to spin it one way, where this one, into the screen was a bad example, but hopefully you can tell what I'm saying, like it's going to rotate about here. These two masses would push it one way. Mass 2 would be pushing it the opposite way, right, if it could rotate here. So to find m sub y, we take all of these together. And we're going to end up with the moment about the y-axis. And then also, we've got to consider the other way too. We've also got this y-coordinate, y sub 1, this y-coordinate, y sub 2, this y-coordinate, y sub 3, because that's going to be these distances going this way, which, along with their masses, would give the tendency for the system to rotate about the x-axis. Okay, so that's the second thing we've got. The second thing we've got is m sub x, which is the moment of the system about the x-axis. Okay, and of course this is the tendency of the system to rotate about the x-axis. And then of course we have a formula. This is equal to the sum I goes from 1 to n, m sub I, y sub I. So the moment of the system about the x-axis, so it's a tendency to rotate about this x-axis, and of course that is going to depend on the masses times these y-coordinates, right? Because those will determine the tendency to rotate about the x-axis. Okay, so we've got a couple of things here. We've got this formula, m sub y and m sub x. So for the center of mass in a two-dimensional coordinate system, it's x bar, y bar, and x bar is equal to m sub y, which is the moment of system about the y-axis divided by m. Remember, m in this case is the total mass, the sum of all the masses. And y bar is just m sub x divided by m. So once again, just as a reminder, this m is the sum of all the masses, right? The sum of all the m sub i's as I goes from 1 to n, and that is equal to the total mass, which is the sum of all the masses, right? Sum of all the masses. Okay, so the center of mass in two dimensions for a finite number of points, x bar, y bar, looks like this. This is how we do it. Okay, so that takes care of center of mass in one dimension and center of mass in two dimensions for a finite number of points. And then we just need to look at the third one, which is the more complicated, which is the center of mass for two dimensions for an infinite number of points. So it's a region between a couple of curves, which is why it has an infinite number of points. So we can't do anything like this. There'd be an infinite number of masses in there, so we can't do something like this. So for this third one, we're going to need some calculus, which I know you've been waiting for, so you'll be glad to see this third one. So this is finding the center of mass of a region between two curves. It is a two-dimensional center of mass. Again, for 3 dimensions, you need multivariable calculus, so some of you will be so lucky that you'll take Calc 3 and you'll see it then. But the difference between this and the last one was this one has an infinite number of points. Okay. So now consider a flat plate called a lamina. Okay, not a word you see every day, but you can practice it. You can practice it at home even tonight. You can say, could you please pass the lamina of potatoes, please? It's a flat plate. So it's a flat plate with uniform density. Another thing that we always need is uniform density. If you want the density to change, that requires another variable. That also requires multivariable calculus. So Calc 3, there's the little, when you do center of mass in Calc 3, you'll have some other things to consider. But for us, we've got this flat plate called the lamina with uniform density, so the density is the same everywhere, bounded by a couple of curves, y equals f of x and y equals g of x on this closed interval AB. We're going to find the center of mass of the plate, which is also known as the centroid of the region. So when you have a two-dimensional flat plate, the center of mass is also called the centroid. And then a little note here, of course, as the density of the region varies, we need multivariable calculus to find the centroid. So for this case, we've got a picture here. So we've got a couple of curves here, y equals f of x, y equals g of x, between a couple of points A, B. And of course, we have got the x-axis and the y-axis. And what we'll do here, we're going to find a little sample strip. So I'm going to just draw a little sample strip here between these two functions. So let's do this. Let's just make a little strip right here. This will be a little strip of this region that we're interested in. And to get some dimensions on this, we'll call this little change here dx, right? So we'll call this little piece will be dx. The little thickness here will be dx. And of course this is easy enough to find. This is just going to be f of x minus g of x. Okay, so if we think of this as a rectangular piece, and of course this is a conceptual idea, we can see it's not an exact rectangle, but as we take limits, we can consider it to act like a rectangle. So this distance here would just be f of x minus g of x, right? This function minus this function, we'll call this dx. And so it says the area of the sample strip above is, so the area is just going to be f of x minus g of x times dx, right? Just length times width, rectangle formula. And its distance, so we're talking about the distance from the y-axis is x. So to get that distance from the y-axis, that would just be this distance x, right? So the moment about the y-axis of the sample strip is, so remember moment, we can think of moment as mass times distance, right? Think of it as mass times distance. That's the moment. Let's head off to the side here and just write something. Okay, we got to get a couple ideas down. So we're going to say moment equals mass times distance. So moment equals mass times distance. And if you remember that rho, density equals mass times volume, right? Well, also, if you have a two-dimensional shape, or like if you're using sheet metal, then you'd be interested in saying density equals mass times area, right? If you're interested in very thin material, think of like a really thin sheet metal or a real thin paper product, you wouldn't necessarily, if you're dealing with sheets of paper or sheets of metal, you wouldn't necessarily think of the density of mass per volume, but maybe mass per area. And if you're selling very thin wire, then maybe you think of density as mass per unit length, right? So although this is the most common, when you see density, you typically think of mass per unit volume. These all three are used for density. But for us, because we're using this flat sheet, we're going to use the second one here. So for us, we're using this. We're going to say density is mass per unit area. Okay, so if density is mass per unit area, well, that implies if I multiply each side by area, I'll get mass equals density times area. Okay, and this is what we need to use. Okay, so coming back down here to finish up what we're working on here, moment is mass times distance. And then if we want to find the moment about the y-axis, m sub y, we could say m sub y equals, well, it's going to be mass times distance, right? Moment is mass times distance. The distance is x, right? And then the mass, we're going to come back up here. The mass is density times area. Mass is density times area. Okay, so this would be, I'm going to write area this way, though. I'm going to write it like this. F of x minus g of x dx, that's the mass, and then the density is rho. Okay, so let me point a few things out. We've got, this is our distance. Okay, so the moment about y, moment is mass times distance. Here's our distance x. Now the mass is going to be the density times the area. Well, we know the area is this, the area of this strip, and then we just multiply by density rho. So just looking at the pieces here, we've got this part is area, and then area times density, that's mass. So now we have the moment is equal to mass times distance. Okay, so hopefully that makes sense. That's how our formula is going to be developed. So of course we want to sum all the strips, right? So we want to sum all these sample strips in here. So to sum all of these sample strips from A to B, we're going to use integration. Okay, and that gets us this formula right here, m sub y. So we've got our density here, and then we've got the mass, right, and the distance. So density we just pull out in front because it's just going to be some number. So the density would be some number, and then we multiply here from A to B. And that would give us the moment about the y-axis. Okay. And then if it happens to be that g of x is 0, we'll explain this in a second, but sometimes there's only going to be one function, not two. So if it happens to be that g of x equals 0, then basically this would just disappear, right? That would disappear, and this formula would reduce to this. So what that means is if you go back up here, it just means that this g of x isn't here. So just ignore this, and then this would come all the way down to the x-axis, right? So this strip would go from here down to the x-axis. So that's when we don't have two curves given, we just have one curve given. Then we can use that simpler formula. Okay, now remember we're looking for the center of mass. So we need to find x bar and y bar. Okay, so from previous work, we had this. We know the x bar is the moment about the y-axis divided by the total mass. Right, so let's just put this in here. So this is the moment about the y-axis. And this is the total mass. And just to make something clear, let me add a word up here. This is the moment if g of x equals 0. Okay. So then we can look up here. So we've got m sub y. We could use this formula. Right, so I'm just going to take this formula here and put it in here. So this would give us the formula from above, and we divide this by the total mass. Well, the total mass, remember what the total mass is? Mass is density times area. Remember from the formulas above, we know mass is density times area. So density is here. Now area, we already know how to find the area. Remember from section 6.1, the area between two curves is top curve minus bottom curve. So the area between two curves, we learned that long ago. That's just going to be the integral from a to b of f of x minus g of x dx. Because this right here is just the area between the two curves. Area between the curves, okay? Now, we can see right here that since these are just numbers, these constants will cancel, so those are going to be gone. But despite what it might look like, these don't cancel. They're not going to cancel that way because this x is being multiplied through here, right? So they don't cancel. So we get the rows to cancel. So then that gives us a formula for x bar, right? Here's x bar. Looks like this. As I mentioned, some of these formulas are a little bulky. So x bar, I'll show you the long way to write it, and I'll show you that it's typically done. So it's going to be the moment about the y-axis after canceling the row. So we'll get basically what we just had above there. So we're going to get the integral from a to b of x times f of x minus g of x dx. And down here we're going to have the integral from a to b of f of x minus g of x dx. Now you can see that this is just the area. This is just the area between those two curves. So because of that, a lot of times you'll see this formula written this way. 1 over the area, and then times basically what's in the numerator. Okay, so you'll see this formula given two ways. This is just a little quicker way to do it because this is always the area. So when we find y bar, we're going to have the same denominator, the area. So we don't really need to find it twice, right? So y bar is also going to have this factor 1 over the area. This is just a little bit quicker way to write it. Okay, so this gives us half of the center of mass. Remember the center of mass, we'll just write this again. Just as a reminder, the center of mass equals x bar, y bar. So we've got half of that. We've got x bar. Now we just have to find y bar. Okay. So let's continue. Hopefully, you guys still awake? Am I just speaking to a void? Hopefully you guys are hearing. My star pupils over here have been sound asleep for a very long time. I don't think, as long as I keep talking like this, they will stay asleep. That's just how it works sometimes. Apparently I have a very soothing voice. I've noticed that ever since I've been teaching. Sometimes listening to me talk about math makes students very sleepy. So hopefully you guys are loaded up with caffeine, maybe one Red Bull in each hand, and you're still with me. Otherwise, maybe just, while I'm rambling right now, do a few jumping jacks, maybe a couple push-ups, and you'll be ready to go. Okay, because we're getting close. We've got x bar, now we just need y bar. So we're going to have to go back to our picture to find the moment about the x-axis of the sample strip. So I'm going to go back to that picture and add something to it. So when you look at this strip over here, see how when we found this x distance, it was real easy because x is the same everywhere here? Well, when you find a y distance, it's not the same everywhere, right? So what we're going to do is we're going to find the middle of the strip. We're going to find the point right in the middle, the midpoint of this strip, and then that's what we're going to use. We're going to use that to find our y value, to find our y distance, we're going to go from the midpoint of the strip. So like this y distance right here is going to be different than the one over here. So if the midpoint of this strip is right here, see how this y value is going to be bigger than this y value, right? So these y values will change. Where x stayed the same here, y is going to change, because this, as you take the midpoint through here, you know, these y values will change all the way through. All right, so it's a little bit more complicated formula, but it's essentially the same. We need to find the area of this, and then we're going to find the mass by multiplying the area times density. And then we just need the distance. So this distance was x. This distance, y, is going to be the average value of these two y values. So we'll basically find the midpoint of that. Okay, so that we've talked about it a little bit. Let's make it official. Okay, so the moment, remember moment, just think of mass times distance. So the moment about the x-axis, m sub x of the sample strip is, all right. And also remember density equals mass over area, which implies that mass equals density times area. So that's the mass. So the moment is the mass and the distance. So m sub x is going to be, I'm going to put y for now. Y times f of x minus g of x dx, and that's the area of that sample strip, right? The area of the sample strip. And then we have to multiply this times rho, times the density. And then this will give us mass, because mass is density times area. Okay? Now, the thing we have to worry about is this is distance. And this is what I was mentioning, that the distance is going to depend, right? So in this case, since the sample strip is vertical, right, the y coordinate, the center of mass, is the midpoint of the strip. So we need to find that midpoint of the strip. And the midpoint of any two numbers is basically just add the two numbers together and divide by 2. So it's going to be f of x plus g of x divided by 2, because this would be like the y-coordinate of the top graph plus the y-coordinate of the bottom graph. We add them together, divide by 2. That'll give us the average, right? So that means that the moment, we're going to have to swap this y out with this. Okay, so it gets a little messier. So the moment about the x-axis of the sample strip becomes this. Again, moment is mass times distance, so we get the moment about the x-axis equals, well, let me copy down what we had first. We had f of x minus g of x dx times rho. But we're going to get rid of this y, and we're going to replace it with f of x plus g of x divided by 2 times f of x minus g of x dx, and then times rho. Well, what we can do right here is we can multiply these together, because this is a plus and this is a minus. That doesn't look like a minus, but let me fix it. It's a minus. So remember that idea of conjugates? When we have something like this, what's going to happen is if we were to FOIL f of x plus g of x times f of x minus g of x, if we were to FOIL those, we would end up, because of conjugates, the outside and inside terms would cancel out. And what we basically get is first times first, which is f of x squared, and then last times last, which would be minus g of x squared. Right, so everything cancels out here. So just to make sure we're okay here, we've got this is the mass right here, or sorry, this is the area, which is the area of that little sample strip, and then this would be the mass, because mass is density times area. And then this part here is the distance. Okay, but when we multiply these together, you can see that this formula will simplify. And you can see where this is coming from. We got the 1/2 here, which a lot of times you just pull that out in front of the radical, or in front of the integral sign also. But get the 1/2 from here. We've got the rho here. When these two multiply together, we get f of x squared minus g of x squared. And then, of course, we got the dx. So this is mass about x. So this is the moment about the x-axis. So this is the moment about the x-axis. And then once again, we're going to simplify this. This is the moment if we've only got one graph, not two. So if the bottom graph really is just 0, or in other words, we don't even talk about it, we just talk about one curve instead of two, then this graph just simplifies because this would just be the x-axis. So it'd be like g of x equals 0, right? Okay, but again, what we're interested in is the center of mass, x bar, y bar. So now that we have this formula, we've got the same situation we were in a few minutes ago. Y bar, what we're looking for is m sub x, which is just the moment about the x-axis, which is the tendency of the system to rotate about the x-axis. And this, of course, is the total mass. So if we fill in what we just figured out up there, we'd have rho, a to b, 1/2, f of x squared minus g of x squared dx. Okay, once again, total mass. Well, mass is density times area, so it's going to be density. And then the area between the two curves, which we know is just f of x minus g of x dx. Again, that's from chapter 6.1. The area between two curves is just top curve minus bottom curve. Right, so this is the area between the two curves. And then we can see again that these densities will just cancel. So we end up with a brand new box here. So we get y bar. Y bar is equal to, I'm going to do it two ways again. I'm going to write it the long way and then the short way that you often will see it. Since those densities just canceled, we get 1/2 a to b f of x squared minus g of x squared dx divided by the area between the curves, which is just f of x minus g of x dx. So what we'll do is we'll just write it in a simplified form of 1 over the area times 1/2, and then a to b, f of x squared minus g of x squared dx. Okay, so then we've got y bar. We already had x bar, so now we've got the center of mass, which again is x bar comma y bar. And then these are the formulas to find the center of mass in 2 dimensions. Once again, this is 2 dimensions, right? 2 dimensions. If it were 3 dimensions, we'd have x bar, y bar, and z bar, right? But we've just got 2 dimensions. And then we can simplify both of these when g of x equals 0. Then they just simplify. There's basically only one function. So when that happens, x bar would be 1 over a, 1 over the area, right? 1 over the area. And then a to b, x times f of x dx. And y bar would be 1 over a times 1/2 the integral from a to b of f of x squared dx. And then these areas we would just integrate underneath the curve between A and B, okay? So now we've got the formulas that we need. So we can find the center of mass for a one-dimensional system, and also for a two-dimensional system with a finite number of points, and also a two-dimensional system with an infinite number of points, which means that this is like the area between two curves. And then we've just got a few little things to mention here that will make life a little easier. There is something called the symmetry principle. And this just means is if a region with uniform density is symmetric about a line L, so if there's some sort of symmetry about this line L, then the centroid of the region lies on L. Thus, the centroid of a rectangle is its center, right in the middle. So remember, centroid just means it's just a center of mass of a solid with constant density. So the density is the same everywhere. So for us, it's just going to be a plate, the center of mass of a plate. Also, when working with triangles, there's a couple things to know. The median of a triangle, that's a line segment from a vertex to the midpoint of the opposite side. The centroid of any triangle is located at the point of intersection of these medians, and the medians intersect at a point 2/3 of the way from each vertex along the median to the opposite side. So I think there's a homework problem or two where this will come in handy. Maybe only one homework problem, actually. This is not like essential knowledge. It just makes life easier. But this definitely makes things easier if you've got, we'll actually look at an example of this. We've got a region of uniform density, which all of ours will have uniform density. When it's symmetric about a line L, then the center of mass of that region lies on that line L. So it'll make life a little easier when this happens. Okay, so we have got an example here to look at. We want to find the center of mass of a thin plate of constant density covering the region bounded by y equals cosine of x and the x-axis. So there's only one function here, right? We've got f of x, but g of x is just y equals 0. In other words, the x-axis over this region. So if you look at example 2, we're finding the center of mass of a thin plate of constant density covering this region right here. So we can see one thing. There's a symmetry here so that we know that x bar is going to be 0, right? So center of mass, so we need to find the center of mass is going to be x bar, y bar, right? X bar, y bar. Well, we can see by the symmetry, and from that symmetry principle, x bar is 0. So the center of mass is somewhere here on the y-axis, right? So x bar is 0, but we'll go through x bar just to show. So let's just find it. We know it's going to be 0, but just for a little practice, let's find x bar. All right, so x bar is going to be, so we've got a formula there. And the formula says it's going to be the integral from a to b of x times f of x minus g of x dx. Now in this case, it's kind of an easier one because g of x is 0, right? So I'm just using the general formula here. And then the area is going to be f of x minus g of x dx. Again, since we've just got this one curve, it's sort of like saying g of x is y equals 0. Okay, so really we don't have a g of x in this case. So what we do have, though, we're going to integrate from negative pi over 2 to pi over 2. We're going to have x times f of x, which is just cosine of x dx. Then on the bottom, we've got negative pi over 2 to pi over 2 of cosine of x dx. Okay, so to integrate this one is going to be parts, right? We can integrate this by parts. So I'm just going to do this up here, just off to the side. So let's say we've got x times cosine of x dx. And if we do parts, and we don't want to be light for class, right? What's going to be u in this case would be the algebraic function, right? That would come before trig, so x is going to be u. So u equals x, dv equals cosine of x, so then du equals 1, and v equals sine of x. All right, so then this integral is going to be x times the sine of x minus sine of x dx. Okay, so that's going to be x times the sine of x, and the antiderivative of negative sine of x is just going to be cosine of x. So then we'll go plus cosine of x plus c. Okay, so that's the answer to this. And then, of course, we don't have the plus c because we have a definite integral. But what we would get is x times the sine of x plus cosine of x from negative pi over 2 to pi over 2. And the denominator is quite a bit easier. It's just sine of x, right? We integrate cosine, we get sine from negative pi over 2 to pi over 2. So let's see, that would give us, we start plugging in values here, we are going to get pi halves times the sine of pi halves plus a cosine of pi halves minus negative pi halves times the sine of negative pi halves plus a cosine of negative pi halves. This is a lot of work for something that we already know the answer is going to be 0. And in the bottom, we're going to get sine of pi halves minus sine of negative pi halves. All right, there's a lot of sine functions here. So if we look at the sine curve here is pi, here's negative pi, and sine goes like this. Oh, it's a terrible picture, but you get the idea. This, of course, is pi over 2, and this, of course, is negative pi over 2. Okay, so looking over here, sine of pi over 2 is 1. So pi halves times the sine of pi over 2 is pi halves. Cosine of pi over 2, that's 0. Okay, so let's see. What are we going to get here? Make a little more room here. Okay, so that would give us pi halves, right? Because this is 1, this is 0. So we go minus. Okay, over here, sine of negative pi halves is going to be negative 1. So this can be negative times negative, which is positive. So we're going to get pi halves. And then cosine negative pi halves is 0. So we just get this in the numerator. Denominator gets sine of pi over 2, which is 1, minus sine of negative pi over 2, which is minus 1. Okay, so we get 0 over 2, which is just 0. Okay, so we just verified what we already knew because the symmetry, we knew that x bar was going to be 0. So now we just have to find y bar. Okay, so to find y bar, this one, we've got a formula for this also. This is going to be 1/2, and then I'm going to put the whole thing in here again, just like before. So I go a to b, f of x squared minus g of x squared dx all over the area, which we just found the area is 2, so that's not going to change. But let me just to make it official, let's put this whole thing in here again. Okay, now once again, g of x is just 0, so these will simplify to 1/2 a to b. This is just going to be cosine squared of x dx. And the bottom a to b meant negative pi over 2 to pi over 2. This would be negative pi over 2 to pi over 2. This can be the same as before. This is just cosine of x dx. Okay. So, all right. When we integrate this one, cosine squared, remember when we have a cosine squared or a sine squared from section 7.2, we'd use an identity here, right? So once again, I'll do that one up here, off to the side, cosine squared of x dx. Well, the identity we use there is 1 plus cosine of 2x over 2, which then we can pull out that 1/2 and we get 1 plus cosine of 2x dx. So we integrate that, we're going to get 1/2 times x plus, now you've probably seen this enough times to know this little u substitution. We have to deal with a 2 and it becomes a 1/2. Right, so we get 1/2 sine of 2x and then plus c. So if you're not sure about this part, just do a u substitution. If you let u equal 2x, then du would be 2 dx, so 1/2 du would be dx, and you end up getting this right here. Okay, so then we plug it in down here, and what we will get is, we already have 1/2 out front, and I've got another 1/2, so it'll give us 1/4 x plus 1/2 sine of 2x from negative pi over 2 to pi over 2. Now this part down here, we already did this one up here above, right? We know this is going to be 2 because it's 1 minus minus 1, so we know this is going to be 2. So I'm just going to put a 2 in here to save a little bit of time. And then we've got to plug in some values. So we're going to get 1/4 times. Okay, we get pi over 2 plus 1/2 times the sine. 2 times pi over 2 is just pi. Okay, then we go minus, and we'll get minus pi over 2 plus 1/2 sine of 2 times pi over 2, which would be negative pi. Okay, let's see, we've got that. I guess that goes here. Down here, of course, we get a 2. All right, so let's see what we've got. This is just going to be 0, right? Sine of pi is 0. Same with this. Sine of negative pi is still 0. So what we get on the top is 1/4 times pi over 2 minus pi over 2, which means plus pi over 2. 2 down here. So that's going to be 1/4 times pi over 2, which is basically pi over 4 divided by 2, which is the same as pi over 4 times the reciprocal of 2, which gives us pi over 8. So that's y bar, okay? So that means that the center of mass is going to be 0, pi over 8. Remember, center of mass is a point, right? It's got an x-coordinate and a y-coordinate. So we need these parentheses to show this is a point, right? The x-coordinate is 0. The y-coordinate is pi over 8. This is the center of mass. All right, so that should take care of the second part of 8.3. It's kind of a long video because there's, it takes a while to explain everything. Hopefully you made it through and are still with me and still awake. Otherwise, have a good night if you didn't quite make it. And you'll just have to watch it again later with some caffeine. So anyway, give it a shot. And of course, as always, let me know if you have any questions.